Hello, everyone. Welcome to the presentation on interconnects for AI Infra and AI Infra for DPU and IPUs. I'm Fani Suresh Paladagu, a product management professional at Synopsis, and my colleague Rajesh is principal engineer at Synopsis. Synopsis is a leader in EDA and semiconductor IPs that can enable our customers for like a silicon to system solutions. Yeah, silicon to system solutions. Today we'll be talking about AI revolution, bottlenecks, interfaces for high performance computing and data centers. Key interfaces like PCIe, CXL, Ultra Accelerator Link, and Ultra Ethernet. Rajesh will be covering high-speed interface implementation aspects as well as the challenges for PCIe, CXL, UA-Link, and UC. We'll wrap up the session with next-gen interface needed for AI Infra, followed by Q&A. So most of the friends and colleagues, like they were talking about like the application level aspects and like more of use cases and things like that. What we are going to cover here is things that happen behind the scenes, like the interfaces that are key for like DPUs, IPUs, GPUs, and accelerators. These are the key interfaces and the protocols like that we'll be using based on the specific use case. So as we are aware, like AI is creating a lot of need for like compute demands and things like that, and model sizes are doubling every 3 to 6 months. So that puts like a multifaceted design challenges. So we have to look at like optimizing the performance, power, area, and the latency for most of these applications. So the increased compute demands puts a lot of pressure on interface and the memory technologies to deliver high bandwidth as well as with a low power and latency. So if you look at the current technologies, 1 petaflop of compute needs like a 3 to 4 terabytes of HBM and up to 1 terabyte of PCI and Ethernet. Like the right side, so with these increased compute demands, like memory standards as well as the interface standards are under a lot of pressure. They need to evolve. And if you look at the graphs, like they are like increasing exponentially. In the past, like each of these standards used to take like a lifetime of like 3 to 4 years. But in the with the current trend and how the AI is evolving, so we have to like, there is a churn of like each standard in like 18 to 24 months. In order to meet the requirements, like the data rates are increasing exponentially. So if you look at the high performance computing domain, like there are 6 primary functions in the SOCs, like accelerators, CPUs, NIC, switches, storage, and retimers. All these 6 primary functions needs bundle of like different interface IPs. If you look at the right side table, like based on the specific functionality, like we need a bunch of interfaces. Like let's start with the accelerator. It needs PCIe interface, Ethernet, ultra accelerated link, memory interfaces. And if you're dealing with the chiplets, then obviously you need die-to-die as well. Look at the NIC requirements, like it needs PCIe, Ethernet, die-to-die and memory interfaces. So these are the key interfaces that are needed, like most of these application the functions. So let me get into the details of the PCIe interface for high performance connectivity. So PCIe is a high-speed interface that will help to data transfer between the NICs to CPUs, CPUs to the accelerators, and CPUs to the SSDs. PCIe is used in like switches as well as the retimers, and it has a wide variety of applications. It can be used in automotive, IoT, as well as aerospace and defense applications as well. So this particular interface is highly configurable, and scalable interface. For example, based on the bandwidth requirements, each macro can support 1 to 16 lanes of PCIe. So if it is meeting, like 4 lanes is meeting our requirements, we can use 4 lanes, or like if you need 16 lanes, we can go for 16 lanes. And if 16 lane bandwidth is not sufficient, and if it is demanding like a more bandwidth in order to meet the overall throughput requirements, we can instantiate multiple 16 lane configurations into the SoC that can get us like the bandwidth that we are looking for. And the PCIe standard is like a backward compatible. That means currently we are at like PCIe Gen 7 running at 128 gigabits per second. So once we design the SoC for PCIe Gen 7, it has to be backward compatible. It should support PCIe 6 and up to like Gen 1, which is at 2.5 gigabits per second. And PCIe supports like low power states as well. So that helps us, for example, if you're not using the link, we can just power down it and like save the power during the idle states. So moving to the CXL, revolutionizing the data center architecture with the CXL. CXL is a Compute Express Link standard that is built on PCIe infrastructure. So it leverages the high-speed path of the PCIe, and it also supports like a few additional protocols in addition to the I/O path. I'll get into the details. So CXL mainly addresses the memory bandwidth bottlenecks in the servers, and it is like designed for optimizing the latency, and like that gets us like low latency when compared to the other protocols available out in the market. So it has 3 different protocols, like a CXL.IO. As I mentioned earlier, it is like alternative to the PCIe. It leverages the high-speed IO available. And CXL.Cache. This particular protocol enables this particular protocol enables the high bandwidth cache coherent access to the memory for accelerators as well as the CPUs. And the CXL.mem protocol enables the low latency access to the memory for the attached CXL devices. So there are like 3 types of the CXL applications, like a type 1, type 2, and type 3. Type 1 is like accelerators without memory. We can take NIC as an example here that leverages the .IO as well as .cache protocol. And the type 2 devices are the accelerators with memory. You can consider as like a DPUs and GPUs are as example. And it leverages all 3 protocols available out with the CXL. The third one is a type 3 device where like we'll be using .IO as well as the .mem application. This is mainly for the memory buffers as well as memory expanders and the pooling devices, mainly to address the memory challenges. So most of you have heard about the scale up and scale out. So Ultra Accelerator Link is used for the scale up applications, as well as Ultra Ethernet is used for the scale out applications. So as the model sizes and the parameters are increasing, so it is very difficult to store all the models within the single GPU or DPU memory. So in that case, like we have to share the memory across the DPUs or the GPUs. And these are the protocols that will enable us to share the models and synchronize between like different GPUs so that multiple GPUs can act as a single giant GPU that can perform the entire task. So Ultra Accelerator Link will enable us the scale up, that is like vertical scaling, and Ultra Ethernet will enable us the scale out, which is like a horizontal scaling. If you look at the diagram here, the one highlighted in the blue is like the vertical scaling that uses the Ultra Accelerator Link, and the one that shows like like between the clusters, that is Ultra Ethernet Link, that helps us to with the scale out options. So for the Ultra Accelerator Link, there are 2 different variants are available out in the market. UA Link 200 that leverages the 224 gig Ethernet physical layer as a baseline, and like the protocol is built on top of it. This will get us the highest bandwidth available out in the market as of today, and that is mainly used for like AI training purposes. And there is another variant, ULink 128. So this leverages PCIe Gen 7 physical layer infrastructure, and this is mainly suitable for AI inferencing applications. So the ultra accelerator link will enable us the direct load, store, and atomic operations between the accelerators. That will save like a lot of time, and minimizes the latency, overall latency contributed by the protocol. The Ultra Ethernet will enable us mainly to address the AI and high performance computing scale out requirements. This is also like a very high speed protocol that leverages 224 gig speeds. And it is also configurable. We can configure from 1 to 8 lanes, and we can have like a multiple 8-lane macros within the SoC to get to the bandwidths that we are looking for. And this particular protocol implements intelligent congestion control for managing the intense burst traffic. This will help us to address the congestion when we are communicating across the GPUs and the DPUs. This is mainly focused on the AI workload, resource sharing, and synchronization among like up to like 1 million endpoints. So if you look at the bottom right diagram, like that gives us like we can have a crossbar connection between different GPUs within the parts and across the clusters. Okay, so I will hand it over to my colleague Rajesh. He will be covering high-speed interface implementation aspects as well as the challenges associated with most of these protocols. And yeah,
thank you.
So, where you said now, when do you think we'll see availability of hardware that actually supports UALink and Ultra Ethernet? Well, that's question one. And question two is Ethernet for scale-up networks versus UALink for scale-up networks. And you just saw the OCP, another set of announcements around scale-up. Everyone seems to be going dog for scale-up these days. Kind of interesting. And so really, the contrast between the UALink approach and the Ethernet approach, how does that play into what you're saying?
Okay, yeah. As of now, like I mean, as I mentioned earlier, we are an IP company. We are enabling a lot of customers with the UALink as well as the Ultra Ethernet as of today. And there are like a lot of vendors and customers out in the market. They are working on these specific, leveraging these protocols. They are designing their SoCs. So there are some customers already rolled out their products with the UALink and Ultra Ethernet at 224. Most of these things are like very early stages. So as I mentioned earlier, like Ultra Accelerator link is mainly for the scale-up applications that can go up to like a few hundreds of interconnecting the GPUs and the DPUs. But if you look at the Ultra Ethernet, that can get us like to up to like 1 million endpoints can be interconnected. So that is at a larger scale, and the UALink is mainly designed for like with a limited set of few hundreds of the GPU interconnections. So within the pod, we can use, for example, if you look at this diagram, within the pod, we can use UALink for interconnections. Yeah. So, yeah. Really good question. I was expecting this like because it was announced like 2 days back, right? So if you look at the scale-up aspect, right, there are 3 different ecosystems available out in the market as of today. Most of us are aware of like NVIDIA NVLink. So they are using their proprietary ecosystem. And Broadcom, sometime back, they announced Broadcom SUE, Scale-Up Ethernet, because Broadcom is they're experts in like Ethernet. So they decided why to use like a different protocol. Let me repurpose the existing Ethernet and leverage for the scale up, right? So they announced like a scale up Ethernet sometime back, and Broadcom, they have their own ecosystem with the Tomahawk switches to enable the scale up using the Ethernet. And the third one, open standard, is the ultra accelerator link. So a lot of market leaders out in the market, they are working on the ultra accelerator link, but the ecosystem is not fully ready yet. But this is an open ecosystem. So once it is ready, I think this can enable like a more openness with respect to like NVIDIA and the Broadcom. So Broadcom, they already have the scale up Ethernet. They collaborated with the OCP. I think that's the reason like they announced like eSun. So I think they are going to leverage the existing Broadcom scale-up Ethernet and like make it like more open and enable to like a lot of other vendors as well. That's my understanding. Yeah, thank you.
And I guess really how all this has something to do with DPUs and standard interfaces by API. Which will be interesting.
Yes. He's going to touch on the implementation aspects.
I always want to jump to the final thing. It's always,
Um,
uh,
Hello, everyone. So I'm Rajesh. So my expertise is in subsystem implementation and interconnect technology like PCIe, CXL, Ultra Ethernet, and UA-Link. So I do designing and I have exact idea in how it's going to fit into SOC. So my presentation is, my first slide is about the PCI interconnect subsystem. Here highlighted in the purple, I have highlighted like PCI subsystem and with the basic building blocks, but the strategy is same for either Ultra Ethernet or UA-Link. That you will have a controller PHY and you'll have a clocking reset structure, control logic and custom logic. So overall, the implementation strategy will be same. So talking about subsystems, right? Like here, if you see, we have highlighted in the purple, the first building block is a controller. Controller generally acts like a brain of a subsystem. This is a protocol specific based on the application. It can be programmed and that it connects to the application logic, which is sitting in the SOC through AMBA bus. AMBA starts for Advanced Microcontroller Bus Architecture, and this is provided by ARM for SOC on-chip communication. And then the next layer is kind of a PCS, is called physical coding substrate. This is a layer which is sandwiched between the controller and the PHY. What it does is it encodes and decodes the data which is coming from the controller side and make sure that it's more reliable and understood by the PHY. Coming to the PHY, so within the PHY, we again have two sublayers. We call it PMD and PMA. So PMD stands for physical medium dependent. It is a glue logic. Along with that, we have a PMA, which is hard macro. So PMA stands for physical medium attachment. So overall, the combination of PHY would be like a PMD plus PMA. The main functionality of is it's any digital logic which is coming from PCS is converted into electrical signals and then it's being transmitted to serial link through PCI link partner. And the data uses a serial bus architecture that uses a lane, utilizes lane for the data transfer. So data which gets transfers are in like a packets, and it has some additional bits being added for encryption and error correction. And this gets connected to the link partner through serial bus. So here, if you see in the diagram, I have like X1 link and X2 link just to show you that when I say X1 link, it has a single lane. When I say single lane, which has TX and RX, highlighted in the orange is TX. The one which is in the blue is an RX. So when we say X2 link, we have two lanes in it. The next slide is about PCIe. I think my friend already covered it, but PCIe stands for Peripheral Component Interconnect. It's a standard component in the computer which is used to connect either network, GPU, or SSD cards. And in this slide, what I want to show is like we have a series of PCIe generation spec releases. if you see, I would like to cover mostly on PCIe 6 and 7. If you see PCIe 6, it has a data transfer rate of 64 giga transfer per second. And when I'm talking about a single lane, it is 8 giga bytes per second. And then for X16 slot, it would be 128 giga transfer per second. Now, the PCIe 6 was released in 2022, and then in the recently, like PCI 7 spec was released in 2025. Here here the data transfer rate is 128. It's almost double the data transfer rate of PCI 6. And comparing to X16 slot, if you see, it is 256 uh, gigabytes per second. So it's a massive increase in the bandwidth. So I would say, like, for every generation of PCI release, the bandwidth is kind of doubling for every generation. Um, Here, what I want to highlight is, like, PCIe architecture is a backward compatibility, and also it can support bifurcation and aggregation of the logic. In my next slide, I would cover about what do I mean by bifurcation and aggregation. Uh, and here, if you take an X16 link, it can be connected into two S8 are like uh, four files, or it may be connected into multiple combination of 4 files. Uh, Coming to the CXL, it's a Compute Express link. It's a totally new protocol which gets added on the top of PCIe. So in the implementation background, the CXL is an additional set of logic which gets added, like apart from the PCI logic which sits in the controller, it has an additional logic which gets added into the PCI. And generally, this logic operating frequency is double the frequency of the data operation. So it's fairly critical when we have a PCIe with CXL protocol. The timing closure becomes very crucial in the design. And I would like to touch upon CXL.io. So it has mainly three sub protocols within it. When talking about CXL.io, it ensures and manages that communicate like a PCI device. And the next is a CXL.cache. It provides a cache coherence to the memory access. So what does it mean is, like, if you see in the diagram on the bottom, like, accelerator can you have a CPU and accelerator, and it is connected through PCIe and CXL bus. So accelerator can access the CPU and cache its memory. Similarly, CPU can access the accelerator and cache its memory. So that the memory between the CPU and accelerator is kind of consistent, and any change in the memory is known to each other. Uh, Coming to the CXL dot memory, so here, like, any device which gets connected through CXL dot memory protocol, it exposes its memory to the host CPU. These are the basic three protocols of the CXL logic. Okay, so this is an important slide because I want to highlight that if you see in the picture, we have a CPUs, we have switches, we have a NIC, a DPU, and GPUs. If you see here, like, PCI is everywhere. PCI is getting connected between CPU to CPU. It is getting connected between a NIC to PCIe switch, DPU to PCIe switch. So in this picture, it is PCIe 6, but it can be PCIe 5, PCIe 6, or PCIe 7. And in my next slide, I would highlight more on the PCIe switch implementation. But what I would like to what I would like to say is here, no, not this. So in the below table, I want to, you know, uh, explain about how PCIe bifurcation logic works. So why I would like to say is because this is a main functionality when PCIe is implemented as a switch. What do I mean by that is in the bottom, I have a physical layer which has 4 files, like 50, 51, 52, and 53, and each one are X4 configuration. And on the top, I have a controllers. As I've shown in my first diagram, the controller acts like a brain, and it talks to the application logic. So the topmost row is a link. The first one is X16 link, X8 link, X4 link, and X4 link. And I have a different mode selection. So what do I mean is, like, irrespective of any mode selection, I'm operating at X16 link configuration. So what do I mean is, like, if I turn on all the PHYs and operate at mode 4, my output would be like X16 link configuration. Now, if I want to turn off Phi 1, Phi 2, and Phi 3 to save power, and I will be turning on mode 3, and then the output still would be an X16 link configuration. In the other scenario, like, I would like to turn on Phi 0 and Phi 1, turning off Phi 2 and Phi 3, and operate at mode 2. So what happens is it grabs 0 to 7 lanes from X16 link, and then 0 to 8 from 8 link, and still operates at the X16 link configuration. So there is a added flexibility here. You know, this is what, like, very important to understand when we are talking about the switches. When next slide is, I would like to touch upon the implementation side here. So I have, in that picture, I have a single monolithic SOC, and it is surrounded by subsystem implementations. Uh, so in this kind of implementation strategy, as a backend engineer, we would like, we generally have two subsystem implementations. One is a north-south and east-west orientation. We need to design in two different formats, and each one has its own challenging. Uh, so here, PCA's switch has three main functionalities. The first functionality is data routing. Uh, what it does is it makes sure that the data packet transfer between the devices are more efficient. And the second one is a bandwidth aggregation. So what does it mean is, like, all the devices which get connected to the PCI switch, bandwidth aggregation happens, and then, like, there is a high-speed data transfer happens between all the connected devices there. And scalability, what does it mean is, like, we have a CPU, but with a limited connectivity and connected to the PCIe. But using a PCIe switch, what it does is it makes sure that it collects all the connected devices and gets connected to the single. So CPU is not limited by the pin connectivity. So that's all about the scalability. And here, before moving on to the next slide, like, when I talk about multi-link subsystem, as I showed in my previous table, I have X16 link, X8, and X4 link. And I explained that I would like to always operate in the X16 link configuration. So here I have some implementation challenges in this kind of floor planning, where all the files are stacked vertical, and I have a controllers which are sitting on the right side. And this is called as a rectilinear cut. When we have this kind of implementations, we generally end up with standard cells, like which are spread. I mean, standard cell is not uniformly placed. They are spread all across and causes cell density and congestion issues. It's fairly complex to implement such kind of subsystem. And the other subsystem, like north and south orientation subsystem, here, if you see the white area, those where the standard cell can be spread uniform, this implementation is fairly straightforward, but it has its own complexity because we are dealing with thousands of clocks here. Uh, Thousands of clocks. So yeah, so the subsystem which east-west is getting implemented on the east and west, and the subsystem on the north-south will be implemented on north and south. Uh,
Time,
Okay.
like, let's switch to, like, the challenges that you can explain,
Yeah,
and
yeah.
then we'll conclude the session.
Yeah,
Yeah, you can just touch on.
yeah. So so this is my last slide. So I was already, like, talking about the implementation challenges. The first one is subsystem implementation. You already, most of the time it's like a macro dominant, IO dominant, and we are talking about millions of gates, standard cells being used. So fairly managing it is very difficult. Bringing up with a floor plan which is more reliable, and then fitting into the SOC environment is kind of challenging. Uh, because they also come in the weird shapes, implementations. And then generally, like, when I talk about implementation in the rectilinear shape, I already touched upon, like, the standard cell placement here, is not uniformly spread. It adds an additional kind of, when you route the design, additional net delays, it adds the congestion hotspots, and then the timing closure becomes very difficult, and we need to have pipeline register for the timing closures. And we have to come up with effective strategies for the timing closure here. And then about CTS thing, right? We build a clock tree, and like generally subsystem would have like hundreds and thousands of clocking structure. Uh, it's always a custom clock tree built to achieve lower latencies and better skew numbers. So it's again a fairly challenging, and at the end, like it's a IR drop and timing closure to the SOC level. So the final will be like once I come up with a subsystem, it plugs into the SOC. Now SOC, it has to function according to the SOC standards, and the IO timing should be like met. So it has its own challenges. So these are my this is my last slide. Any question? Yeah.
Yeah. Today we'll conclude with the final slide. I'll just show the next generation interface solutions for the AI infra. So earlier we were talking about PCIe Gen 7 at 128 gigabits per second. So that standard was ratified like mid this year. At the same time, in a different room, PCIe SIG announced like a PCIe Gen 8, which is operating at 256 gigabits per second, which is double that of like PCIe Gen 7. So we are expecting that standard will be fully ratified in 2027, and then like people will start using it. And if you look at the ultra accelerator link and Ethernet, currently it is at like 224 gig data rate, 224 gigabits per second data rate, and these two standards will be moving to 448 gig by 2027. And there are like some additional security features also introduced into these standards. So if you look at the die-to-die or the UCIe protocol, right now it is at 32 gigabits per second, and it is transitioning to like a Gen 3, which is at 64 gigabits per second. And not only, I mean, this is mainly for like 2D applications. In addition to that, we have to look at like multi-die options and the 3D and 2.5D applications, where we are looking at like 3D IOs and the 3D compatible like UCIe IPs. This concludes our session. Thank you.
Thank you, Fani, and thank you, Rajesh.
AI's mission and what we would like to see from an API is a part of all of these AI networks and components. And I would argue 802.3 is the 224.48 transition and not VC. We see some certainly protocol and minor physical layer efforts that are being pushed in IEEE.
Yeah.
So UEC itself doesn't actually push that transition or linear pluggable logics or things like that. But that aside, what of this ties into OPI and common APIs, common lifecycle provision, common application use cases, especially on accelerator fault codes? How do you tie your whole presentation back to OPI's mission?
Yeah, I mean, like, see, all these interfaces are highly programmable based on our bandwidth requirements. We can come up with the specific configuration, and that will help us tie into the OPIE, the main goals. So, for example, like as Raj explained, like if you're looking at an accelerator, you can have like a by 16, I mean, 16-lane configuration of a specific protocol, or like if you're looking at the switch configuration type of thing, like wherein you'll have like hundreds of lanes. So these are like modular designs and can be configurable based on the specific use case. Most of these protocols, that's how like it will fit into the main goals of the OPI.
So are you suggesting that the place that we can take OPI is into the system bus and component chip configuration at the system level, as opposed to worrying about, putting stuff on DPUs and that.
I did not get the last point, like, yeah.
So what OpenAI's done so far is said, given a data processing kit, which,
Yeah.
you know, Vincat showed our diagram that defines kind of the envelope of what a data processing kit is on the very first slide. What are the things that can enter the way applications could be commonly loaded across multiple vendors in the implementation of that or architecture, despite, you know, variance in, you know, how many architectures or how much they're building, which things are accelerated in hardware, which things are not, and all of that. So OPIs have the mission to provide the common APIs with that infrastructure. OPI has not really ever said we ought to have one, we ought to tackle direct configuration of the IC interface, other than where they touch use and the virtual functions that are DPUs on PCIe and things like that. So are you suggesting that a place to take OPI is into the multiple types of high-speed interconnects that are especially being leveraged by AI systems, and that there's value there and an interest in commonality, given all these different standards out there, the different commonality of doing good things for that?
Yeah, I mean, our main interest, as I mentioned earlier, right? You all were talking about the application layer and like how the system can be used in like in the real scenario. The interfaces that we were discussing here are like needed for like a DPU and the accelerator designs. Those are being used within those designs. So how this particular DPU can be like, I mean, leveraged at the system level based on that requirements, like we can use like all these interfaces. That's what I meant. These are like the key ingredients needed for the DPU and the accelerator and GPU designs. The back end.
And I'm just trying to understand and see how that relates back to what, okay, yeah, okay, well, I'm going to be cross questions. Thank you.
So I have,
I know no DPU, but they do anything. Well, every DPU has Ethernet, not all. I mean, they have Ethernet. They have Ethernet IP, and everyone has a roadmap and they tell you which data.
Sorry, 1 minute pause it on.
No, it's okay.
Right, so this is very
It's okay.
complicated. That's my question, because now, if you say, well, accelerators will have all these interfaces, and they ought to be configured in play, maybe that's interesting.
You want to use mic for the online audience?
So,
Yeah, good.
yeah, so, yeah, the question is there an interesting high that we all explore?
Okay.
Technical steering committee or what's being said here that does a few things. One, it expands the scope of OPI a fair amount, but it also maybe gives OPI another reason to exist in that common ways of setting up these things across GPU server vendors, maybe there's a place to go, except that the counter to that is all of the people involved in all the standards that are behind these nice colored boxes on the right, all think they're doing that internally and don't really want something common that's overlaid across all of those things, either at the hardware or the protocol level. At least they haven't historically. In the history of the industry, there hasn't ever really been that. I mean, it's something to think about. But
yeah, I was wondering the same when they're actually discussing this, like how this ties to OPI. So here's my take on that. So for UAL, I think OPI doesn't make any sense. But for UEC, maybe things like programmable congestion control on the interface can be configured via OPI. to the NIC.
Yeah, we certainly have guide to configure those. The challenge you have there is that, of course, UDC has an entire API group. That's defining all the APIs to configure over Ethernet transport protocol as well as the INC. There's an entire work stream, an entire group within UDC that's defining those things.
Yeah, right. But if we are
I'm
looking
really
at-
sorry, Vijay, because of time, we are already running 25 minutes late kind of a thing. So I'm really sorry, Joe. So we'll continue. We cannot compromise on the lunch time, right? So we'll move on. We'd like to thank both Funny and Rajesh for the call. Thanks a lot.